My method for aligning telescopes requires several pieces of equipment. The first item is a precision ball bearing, which is supported in a way that allows it to be placed at some desired location, some distance from the telescope. The second item is a good quality helium neon laser. The third is a small mirror mounted on a precision 2-axis tilting adjuster. There are also ancillary items such as 2 sturdy tripods which can support the laser and the ball bearing, and a mechanical base which provides a rigid connection between the laser and the mirror adjuster. You will also need an appropriate high-quality eyepiece for this test. You also need to have a long extension barrel for the eyepiece used on the telescope. Because the object you will be viewing is much closer than infinity, the image will be formed farther back behind the telescope than it would be if you were looking at a celestial object. Next, I'll provide more details on each of these items. The first item is a precision ball bearing. I use a 3/8 inch chrome steel ball bearing, which is rated grade 5. This grade guarantees an extremely good sphericity and a very low surface roughness. This ball is held in place by a small magnet on the end of a steel rod. That rod is attached to a tripod. You can use any convenient method to attach it. You want the rod to be vertical with the ball on top, as shown here. You'll need to adjust the tripod's height so that you can point the telescope at the ball bearing and have the eyepiece located at a convenient position. I prefer to have the telescope pointed horizontally. For this test, I recommend you sit in a chair while viewing through the eyepiece. This assembly should be located approximately 80 feet to 100 feet from the telescope under test. This might be the most challenging requirement for some test locations which don't have a clear path. The problem is, the closer the ball bearing is to your telescope under test, the longer will be the extension barrel required for the eyepiece, and this gets rather messy. In any case, wherever you set up the telescope and this equipment, be certain that the full aperture of the scope has a clear, unobstructed line of sight to that ball bearing. I keep my laser and its power supply in a good case for their protection. The laser I use is a helium neon gas laser made by JDS Uniphase. It's a self-contained unit with the plasma tube and high-voltage power supply module incorporated in a small case weighing only 4 pounds. Its output beam exhibits random polarization modes with a 0.8 milliwatt beam power. The beam exhibits low noise, and its mode is predominantly the fundamental. The small external power supply inserts into a wall outlet and provides low-voltage DC to the laser unit. I like this laser because it provides a low-noise beam with sufficient power and a nice, clean Gaussian beam cross-section for my application. It warms up to full power output in only 10 minutes. That laser beam needs an accurate steering method so that you can place the center of the Gaussian beam directly on the ball bearing. Rather than move the entire laser unit around, I chose to steer the beam optically. It's done by using a small front surface mirror mounted on a precision 2-axis tilting mirror adjuster. This particular mirror adjuster is made by Newport Optics. The mirror is a small square form with a luminized front surface, and it's bonded onto the adjustable plate. These knobs on the rear side allow you to tilt that mirror in the vertical and horizontal planes. I built a small base using an inexpensive optical rail and components made by Thorlabs. One could use any convenient materials to make a base. Mount the laser and the mirror adjuster rigidly so they don't move relative to each other. When the laser and mirror adjuster are mounted on the rail, they look like this. The laser beam will reflect off the mirror and head towards the ball bearing. You can set this to any convenient angle by installing the mirror adjuster as you wish. Then the user can steer the laser beam accurately by slowly turning the two knobs on the Newport adjuster. Using this method, you can position the center of the Gaussian beam exactly on the ball bearing. I find this saves some time. Incidentally, this optical rail is mounted on a second tripod, so you can position it close to the ball bearing. Place the tripod and laser slightly off the optical line of sight to the ball. The steering mirror can be 3 to 6 feet from the ball, which will result in a bright red artificial star for your test. This is the long extension barrel I use to access the focal plane during the test. Remove any star diagonal from the telescope. You want to view the artificial star image directly on the axis of the scope. There's 2 features about the extension barrel which you need to have. On the front end, there are internal threads which allow you to screw this barrel onto the visual back adapter on the rear cell of the telescope. This aligns the barrel with the optical axis of the scope. On the rear end, the barrel accepts an adapter tube which can hold a standard 1.25" ocular. An ocular is what we commonly refer to as an eyepiece. The ocular is one of the most important components of the test scheme. You need to have a sharp, highly magnified view of the artificial star image to accomplish the final steps of the adjustment. Typical oculars which astronomers use to view with their scopes will not be sufficient to this task. This ocular needs a very short focal length in order to provide the magnification you need. And it needs to provide a high contrast image so you can properly see and evaluate the energy distribution in the diffraction rings. For this purpose, I use a Takahashi MCLE5 ocular. This ocular uses multi-coated extra-low dispersion optics and provides a long eye relief even at the 5mm focal length. Its images have very high contrast. It doesn't have a wide field of view, but for this application you don't need a wide field. What's really important is that 5mm focal length. You should also have a second ocular handy, which has low magnification and a fairly wide field. This is used for the initial steps of the adjustment when you're just positioning the central obscuration. Any convenient ocular, for example a 26mm Plössl design, should work well for this part of the adjustment.